Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And the idea again comes from one of my subscribers, and this may not be exactly what they were looking for. And if it's not, I can also go back and do this a different way. But the main question was, how have weather forecasting techniques changed over the years as it relates to a major event or major events? And this particular event that I'm going to talk about today, probably none of you would know anything about, but it was very significant during the time that I was at Penn State, and I think it'll give you a pretty good idea as to how far we've come since the late 1970s. So you go, from 1979, you go to 89, 99, 2009, 2019, 2024, 45 years. And certainly our computing capability has changed immensely over that period of time. So let's go on ahead here, and I'll put myself in the corner. And this is just for fun. This has nothing to do with weather prediction. But when I was up at Penn State, I was one of the people that took the official weather observations at the weather tower. That weather tower was actually on the top of a building called Dike Building. In 1975 and 76. And then in 1977, a new building was built called Walker Building, and we moved over to that building, and the weather observations were taken there from that point forward. But all of these little cards indicate the observation taken on the morning of that particular day. And so this was July 29th of 1979, and this was the very last weather observation that I took at Penn State. I had graduated by that time, but I hung around the university for a good part of that summer and worked for the weather department or meteorology department. So my initials down here, observer, GBF, which stands for Gregory Buchanan Fishel, and so that was the last observation that I took almost 45 years ago. So a little bit of reminiscing there. All right, so important things to know. In 1979, one of the main models that was used back then was called the LFM, which stood for Limited Fine Mesh Model. And back then, we thought that the grid spacing was fairly fine. Now it's pathetic compared to what we have now. But in 1979, the model resolution, or the grid spacing, the spacing between the grid points where all the equations are solved, was 127 kilometers, or about 80 miles. Now, typically, whatever your grid spacing is, you can only resolve features that have a wavelength of about 4 times the grid spacing. So that means that back then, the model could only resolve waves with a wavelength of about 4 times the grid spacing, or about 320 miles. So anything that had a wavelength less than that could not be resolved. And so this is analogous to you having a camera, and I think I've used this example before. You're looking across a lake, and there are 4 houses there. But if your camera has a really, really poor resolution, you're going to see those 4 houses as one house, okay? As the camera resolution gets better and better, then maybe the 4 houses become 2, and then 3, and then eventually, if the resolution gets good enough, you can see all 4 and see all 4 very, very clearly. So back then, the models were like a camera that had really, really poor resolution. Now today, the GFS model, or the American model, has a resolution of 13 kilometers, or about 8 miles, okay? So we're talking about from 80 to 8, okay? And the European model has a resolution of 9 kilometers, or about 5.6 miles, okay? And so that means they can resolve waves with a wavelength of 32 and 22 miles respectively, as opposed to the 320 miles that the main model that we used back in 1979 had. And then there are what we call high-resolution convection allowing models, and those have resolutions as low as 3 kilometers, which actually allows them to simulate individual thunderstorms. Now, I'll just digress here a little bit on this, is that we've talked before about how on the large scale, we can assume a balance of 2 forces in the atmosphere. The pressure gradient force, which is directed upwards toward lower pressure, from high pressure to low pressure, and the force of gravity, which of course is directed downward. So if the two forces balance, then that means you have no acceleration, okay? Force equals mass times acceleration, and so if there's no net force, there's no acceleration. However, we know with thunderstorms there are huge accelerations going on in the updrafts of these storms, especially the stronger ones. And so convection allowing models actually account for the fact that there is an imbalance of forces within these thunderstorms, and they are called CAM models, or convection allowing models, and they operate at a very, very high resolution and actually have the ability to try to simulate individual thunderstorms. We're still not at the point where they can say, yeah, tomorrow at 2:57, that first thunderstorm is going to pop over this house. Okay, we can't do that yet. We're not even close. But at least we're heading in that direction. So the difference between then and now is absolutely remarkable. Now, there was a Saturday night, and I guess it was January, it would have been late the night of January 8th. It was a Saturday night in 1977. And this was the 48-hour forecast that came out from the LFM model, the limited fine mesh model with that resolution of 127 kilometers or about 80 miles. It had a 967 millibar low close to Atlantic City, New Jersey. If you can't see that well, Pennsylvania is up in here, North Carolina is down in here. And so here's the low. And we were just cold enough, at least the model forecast was just cold enough so that everything we got was snow. And it gave us about 2 inches of liquid equivalent, which would have been about 2 feet, okay, in State College. Well, we all thought that we were going to get absolutely lambasted and that the university was going to have to close and it was going to be one of the biggest, storms of all times. Well, and these are the kind of maps that we looked at back then. These were wet paper facsimile maps where you had a facsimile machine that had wet paper and a helix would spin around and make contact with this metal bar and burn the image into the paper line by line. And we only were able to look at model forecasts every 12 hours. So 12, 24, 36, and 48 hours, and only for about 5 or 6 different parameters. That was it, okay? So up in here, these lines that sort of go around like this were vertical motion, telling you how strong the upward motion was in the atmosphere, and it was huge over southern Pennsylvania. And the other lines here, I believe, I'm trying to look at this here, actually were precipitation amounts or contours of equal precipitation, okay? And so the biggest one of those was up in here. So that's what the actual forecast looked like. Now, when I woke up the next morning, I called the weather observatory, and whoever answered the phone said, well, they don't seem to be quite as excited about it now as they were last night. And I'm sitting there going, oh my gosh, here we go. So I ran into the observatory, and the new model run came out, and instead of taking the low up over Atlantic City, it took it up over Akron, Ohio. Okay, that's quite a difference, and it put Pennsylvania on the warm side of the fence. So we started as snow, but then we ended up warming up aloft and ended up changing over to sleet and freezing rain and then stopping, okay? So instead of getting 2 feet, we ended up getting, I think, a little over 5 inches with a nice sleet coating on top of it. When this particular map was analyzed, and I don't have a time on this here, it still looked like there was a chance that this low developing down on the Gulf Coast here was going to slide eastward and then head up the eastern seaboard. But what ended up happening is the low actually went west of the Appalachian Mountains up over Ohio. Eventually, a secondary low did form along the east coast, but it was too late to save central Pennsylvania from the turnover to sleet and freezing rain and then the precipitation coming to a grinding halt. So here you see the eventual outcome of all of this is that the first low went up here over Ohio, and then a second low formed off the mid-Atlantic coast. Eventually this one took over, but again, it was too late to do us any good in central Pennsylvania. So the thing is, if you think about this, the change from an Atlantic City track to an Akron, Ohio track, you may think is huge, and it is, But the grid spacing back then was so crass, okay, it was the grid spacing was so large that if you think about it, it probably only changed the track of the low by maybe 1 or 2 grid points, okay? Now, with the higher resolution models, you're not going to see those tremendous changes from one model run to the next because you're able to resolve the features much, much more effectively. And so any changes are going to be very, very subtle compared to what we experienced on that particular day. But one thing I will mention, and some of you have probably heard this name, Joe Bastardi was one of my classmates. He was a year ahead of me. And when the first model forecast came out Saturday night and gave us 2 feet of snow, we knew that eventually he was going to come up to the weather tower because that was Joe. I mean, he just always kept up with what was going on and has a memory like a steel trap. I mean, this guy can remember weather events, you know, back 40, 50 years, right down to the detail. So anyways, we decided to play a trick on him. And we said, when Joe comes up the stairway, we're all going to have this sad look on our face, okay? Like everything looks really, really bad. And so he comes up the stairway and he said, why are you all looking so sad? And then he goes in the teletype room, okay? We had 2 Western Union teletypes, which are like typewriters connected to a phone line. And the raw model output was on these teletypes, on the paper the teletypes were printing on. And we watched his reaction when he went in that room and he looked at the model output. And it sounded like, I don't know how to describe it, but I mean, he just started like screaming and moaning and you know, he just thought, oh my gosh, this is like all of our dreams come true, you know, massive snowstorm in central Pennsylvania. And nobody was more disappointed than him the next night. In fact, I remember him being in the teletype room and the observation from Elkins, West Virginia came in, and it was 25,000 scattered, which meant that the only clouds that existed were up at 25,000 feet and they covered less than half the sky. And he looked at that observation and he said, it's a beautiful evening in Elkins. And it was, okay? But that's not the way it looked like it was going to be the night before. And so wild variations from one model run to the next back then because of the crass resolution. But now, thankfully, the changes from one model run to the next are not nearly as big because the resolution is so much better. Okay, I know that was long, but it was an event that I will never forget for a number of reasons, both personal and scientific. And so I thought you might enjoy me sharing at least a little bit of that with you. All right, folks, that's it for now. You have a wonderful Wednesday evening, and we'll talk to you again tomorrow. Take care.